The equation we need, we're going to predict IQ at age 16 from IQ at age 8 with a correlation of 2/3. So the equation is z hat yi is equal to rxy z sub x sub I. And we're given all the values so we can plug in. We have y hat I minus 100 divided by 15 is equal to 2/3 times the z-score for x. And the z-score for x, if the kids at age 8 have IQs of 70, the z-score will be 70 minus 100 divided by 15. Any questions about how to set up the problem? So the equation we needed is the prediction equation. I simply substitute in for what's the z-score of y hat. We're given the mean of y, the standard deviation of y, correlation coefficient, and the mean of x, standard deviation of x, and the value of x to predict it. Any question about that? We can multiply both sides by 15. So we have y hat I minus 100 is equal to 2/3 times minus 30. And 2/3 of minus 30 is minus 20. So we can add 100 to both sides, so we get y hat I is equal to 80. How many got that? Okay, so it looks like about half maybe. Questions about it? Any questions about how you do it? You need to know the prediction equation. You need to know what the equation is for the z-scores. You need to be able to substitute in and rearrange for the solution. Any questions about how to do it? So if you pick kids who at age 8 have IQs of 70, what do you expect them to do by age 16? Increase. Increase by how much? In this case, if the correlation is 2/3, you expect them to increase by 10 points. How about if we had a program here where we took 8 kids whose IQs were 70, we put them in special ed and they went up to 75. Would that be a good program? Now hopefully when you saw this right here, you said, uh-oh, that's not an experiment. You need a control group to have an experiment. You need to take these kids and randomly assign them conditions and leave one group alone and then put one group in the treatment group and compare the two. Why? Because of what's known as spontaneous remission when they're sick. Remember, most people tend to get better without Brownian differentiation from their colds. Where's the student who had the cold? Is she still here? She didn't die? See, there she is, yeah. You survived, right? Got better. Most people get better with Brownian differentiation therapy. But most of these kids would have gone up, on average, they would have gone up 10 points. And here's a program that they only go up by 5 points. So this would be an argument that it's a bad program. Why did the scores go up? Paradoxical, isn't it? It's called regression to the mean, and it's a consequence of the fact that the correlation is less than 1. Can a correlation be greater than 1? No. Correlation between minus 1 and 1. It can't be. It has to be something. For any real variables you're measuring that aren't perfect, your correlation is going to be less than 1. It's going to be in the range from minus 1 to 1. So it can't be greater than 1. So you expect regression to the mean. You always expect regression from what you know to what you don't know. We do, they were 70. But we don't know what they're going to be at 16. So you regress to the mean. Now how about if they were 130? What do you expect is going to happen when we predict to 16? Well, the thing is going to be set up in the same way. We still have the same equation, but instead of 70 here, the only difference is we'd have 130. Everybody agrees? So we just write the prediction equation, we substitute in. Now our x value is 130 instead. We multiply through by 15 and we get y hat I minus 100 is equal to 2/3 times 30. Because 130 minus 100 is 30. 2/3 of 30 is positive 20. So that means that y hat I is equal to 120. So what do we expect the kids whose IQs are 130 to do as they get older? Go down. So as the kids get older, their IQs go down. As these kids, what happens to these people? They go up. What happens to these people? They go down as they get older. How about if the GATE program, the kids end up with IQs of 125, showing a 5-point decrease? Is that bad? No, that's good. We expected them to go down to 120. Again, we should have had a control group. You want to do this right, you should have a control group. I've talked to junior high school principals. Any of you planning to be a junior high school principal or a teacher who might become a principal someday? I've talked to junior high school principals who say, we have these kids who are young and we put them in the GATE program, and what happens to them? They go from being an A student to a B student. We think it's because it hurts their self-esteem to be in with the other bright kids. I say, that's just regression to the mean. She says, what? Never had intro psych, did you? Anybody that's had intro psych knows that if you take bright kids, no matter what you do with them, what are they going to be like 8 years later? They're going to not be as bright. It's not going to seem as bright as they did when they were 8 years old, because you picked them to be bright at 8. You picked the tallest kids at age 8. Are they getting shorter? No, they're getting taller. But are they going to be the tallest adults? No. They might be the tallest kids at age 5, but they're not necessarily, they're taller than average, but they're not necessarily relative to other people. They've gotten shorter. Other people have gone by them. So they're not going to be the tallest kid anymore. They're going to be tall, but not as the tallest. The children of basketball players, are they as tall as their parents? No, they're regressed to the mean. The children of gymnasts, are they as small as their parents? Gymnasts are small, in case you didn't know. We're not doing gymnastics now. What are we doing? March Madness, right? UCLA wasn't supposed to make it into the tournament, but they won their games. People said, oh, they didn't deserve to win the game because the guy was goaltending. They called it, you know, for a change. At the end of the game, they called goaltending. We had wrestling championships. But in gymnastics, what do you have? You have small people. They're little. They tend to be light. Why? Because they have to lift themselves up on the parallel bars or on the rings. You know, the men or the women have to be able to balance on a little skinny beam, walk along and do tricks on there. So they tend to be really small. When they have children, 2 little gymnasts, the kids are bigger than they are. The children of football players, they're not as big as, you know, the linemen, football linemen, when they have kids. So we have regression to the mean. So these kids, as they get older, the ones with low IQ are increasing as they get older. The ones with high IQ, they're decreasing. They're showing regression to the mean. How about the kids who end up? Well, the prediction equation works exactly the same way, but it's paradoxical. So now we use the equation, if we're predicting x from y as z hat xi is equal to rxy z sub y sub I. So now we want to predict what their scores at age 8 are going to be from their scores at age 16. What were the kids who end up at, the ones who end up at 70, what was their average IQ at age 8? Well, it works exactly the same way. So the answer here was 80, they increased. The answer here was 120, they decreased. The answer here, you're just going to plug in the same numbers, and if they ended up at 70, what was it before? 80. What happened as they got older? They decreased. So the people who end up 70, they were decreasing in IQ as they got older. We regress from what we know to what we don't know. We know they ended up 70, so they were higher before. So they've been decreasing as they get older. And the people who end up at 130, they were 120. So they were increasing as they got older. So the kids who end up tall, they were increasing relative to other people. The kids who start tall, they decrease relative to other people. The kids who start low in IQ, they increase relative to other people as they get older. Kids who end up low in IQ, they were decreasing relative to other people. Always regress from what you know to what you don't know. So if you had trouble with this and didn't do number 17, the assignment is to go ahead and do it again. Again, these numbers, it looks like when I wrote this down, I should have put 1/3 in there. The problem, the way it's set up is there's X and W and Y, age 8, age 12, age 16, and the correlation between 8 and 12, I think I put in as 2/3. Correlation between 12 and 16 of 2/3, and the correlation between X and Y of 1/3. This number is smaller than it really is, but I wanted nice round numbers for you so that the problem would work out nicely for you. But the correlation between two IQ tests given close together in time is higher than between two tests given farther apart in time. So if you test people 8 years apart, you get a lower correlation than if you test them 4 years apart. And I'll be going over that more with you. So the exact numbers aren't going to work out for you because I put 2/3 here on the board instead of 1/3. Any questions about that problem or how to interpret it? It's paradoxical. Again, I told you already, this is known as Galton's paradox. And remember, the word regression to the mean came from this wrong theory of genetics that we no longer believe in, but we believe in the theory of statistics, which explained the result that he had. The theory of genetics implied that the variance in all measures should decrease over time. And it isn't decreasing over time the way it should under the blood mixing theory of genetics. And basically we know that theory is wrong. On the other hand, under Mendel's laws of genetics, the variance does not decrease. So that's just what Darwin and Galton needed for his theory of evolution, but confused himself with his wrong genetic theory. All right, any questions before I erase that? Question?
This is applicable to group data, but you couldn't actually predict one individual very accurately.
Well, if you would predict for one child, there would be variability, right? So if you picked one kid, the odds are, not every kid. So we have a correlation of 2/3, right? And if the correlation is 2/3, how much variance do we get off? 2/3 squared, right? Less than 50%. That means still 50% of the variance is left. So you would make a prediction if there was one kid whose IQ at age 8 was 70, and the correlation is 2/3, we're predicting something with the 2/3, you predict it's going to go up to 80. Is everybody going to go up to 80? No, some of them are going to decrease. Most of them are going to increase. Your best bet would be that it's going to increase. The average value of the kids like that is going to increase, but not everybody's going to increase. How much variance is left over? Well, you get r squared off. That means you have 1 minus r squared left over. Multiply that by the original variance. That's how much variance is left. So if you wanted to predict the whole distribution or make a distribution confidence intervals on your prediction for that one kid, you would take not just the predicted value, but also the variance, what's known as a standard error of regression, and use that to get your confidence intervals. So you could say plus and minus 1 standard error with 68% confidence, plus and minus 2 standard errors of regression with 95% confidence. When you take a stat course, we're not going to do confidence intervals in here, but take a stat course, they'll certainly teach you about all that. All right. Any other questions before we erase that? Now, what was the problem that Binet had? Remember, what was he trying to do? What was his problem that he was trying to solve? His problem was a practical question. Practical question involving educational policy. And the practical problem was some kids were falling behind in the public schools. And you want to do something to try to fix things so that they don't go farther and farther behind. What can you do? Well, you think there must be some sort of special ed, some sort of special intervention. how do you predict which ones are going to fall behind and give them the intervention before it's too late? Rather than wait until you have a failing situation, try to intervene and do something ahead of time. And so his problem was he wanted to predict, and he tried the kind of tests that Galton and others had been trying, and they failed. And then he got this insight. So here was Binet's insight. If I want to predict which kids are going to do better, I should use tests that differentiate kids according to age. The bright kids are like older kids, but just at a younger age. So bright kids, the ones who are going to succeed, they're like older kids. In other words, they can do things at an earlier age. And so he picked his tests to differentiate or discriminate by age. So he selected with age. Let's take an example of one of the tests that he has. Here's what you do. You give a kid, small child, pencil and a piece of paper, and you say, I want you to copy this square. And at a young age, kids do stuff like this, and then they are able to do stuff like this, and they create shapes like that. And then they start being able to do stuff like this. That would score wrong. And then at some point they get better, and even if it doesn't quite fit exactly, but it looks something like that, that would be scored as correct. So the job is to copy this, copy a square. The younger age, they're doing this sort of thing. Then they get older, they can do things like this, and they start generating stuff like this. Then they start generating lines, but they don't get the right number of sides on it, and then they get something that will be scored as correct. And so if we plot the percentage of kids who get it correct as a function of age, we see that below a certain age, very few of the kids can do it, and then at some point it goes up, and then it levels off, and kids above that age can do it. And the age 5 is where you see a big change in slope. So right around the age of 5, kids go from not being able to do it to being able to do it. The percentage of kids who get it right increases. And so what he did is he picked tests that were like this. This is copy a square. And items that are more difficult are going to be farther out, so the kids still can't do them at age 5, and then they start being able to do them at a later age. And the tests that are easier, the kids are able to do it at a younger age. So items that have curves like this, that vary as a function of age. If you have items like this that everybody can do and it doesn't depend on age, this is not a good test for an IQ test. This is not the kind of item that he would have picked. Are ones that decrease as the kids get older, they get worse on the item. The ones he wanted to pick are the ones he picked are the ones that increase. The percent getting it correct increases with age. So let's take a look at what he found. What could the average 5-year-old do? Everybody clear on the idea? This is his key insight. He wants to, what is it he's trying to do again with the test? Predict success in school. And what's the idea that he has? That it should be, he should pick tests that correlate with age without looking at theories about nervous systems and being able to discriminate tones or how much weight you could lift or how much shock you could stand or any of these other kind of things that other people thought. So at the age of 5, here's some of the kinds of tests that Binet came up with. average 5-year-old can fold a piece of paper 2 times to make a triangle. So you give the child a square piece of paper, you fold it over once, that creates a triangle. Then you fold it over a second time, that creates a triangle. Say, I want you to do this, you give them another sheet of paper, another square, they have to fold it over once, fold it over twice, make the triangle. Draw a man with a missing leg. Define 2 out of 3. Hat, ball, stove. Say to the kid, I want you to draw a picture of a man with a missing leg. And if they draw something like this, you say, what's that? And they say, oh, that's his missing leg. Okay. On the other hand, if they just draw a regular man, then that would score wrong. I want you to tell me, what is a hat? And the kid says something like, a hat is what you put on your head. That would qualify. What's a ball? A ball is round, you play with it, like a basketball. What is a stove? Stove is what you cook on. Right? So if a kid could define 2 of those 3 words, they score at the 5-year-old. Copy a square. We just went over that one. Explain similarities and differences in pictures. And assemble 2 triangles to create a square. So you have 2 triangles. You show the kid, here, look, these 2 triangles fit together and make a square. Then you take them apart, turn them around, and tell the kid, why don't you put them back together and make a square. Now, if the kid can do that and nothing else, they're said to have a mental age of 5, whatever their chronological age is. Now, let's say their chronological age is 2.5 years. What do we mean by chronological age? So CA is going to stand for not California, but chronological. Like a chronometer is a clock. Chronos is kind of, the god Saturn. It's another name for Saturn. And Saturn is a planet that the ancient people saw that it moved pretty slowly through the sky. So they decided that he has to do with time and things that take a long time to happen. Putting something in chronological order means you put them in order of time when they happen. So chronological age is like your clock age. So if a kid is exactly 5 years old, his chronological age is 5, but mental age that corresponds to how well you do on the test. If you can do these items and no more, you have a mental age of 5, whatever your chronological age is. Now, if the kid is actually 10 years old and can do these items and no more, they're 5 years behind. They're way behind. But if the kid is 2 years old and can do these things, that kid is way ahead, right? And Binet talked about years behind and years ahead and so on. Now at 8 years, the kid should be able to define words like these: orange, straw, and top. Remember story content. So for example, we'll do a little 8-year-old item here. I'm going to tell you a story. The name of the story is The Wet Fall. Johnny went riding on his pony. He came to a stream, and his pony stopped, and he fell off his pony in the stream, and he got wet. And he stood up and got mud on himself. He got back up on his pony, and he rode home. His mother said, "You're wet, and you have mud on your shoes. What happened?" He said, "I fell in the stream." What is the name of the story? The Wet Fall. That's right, all at once. 8-year-old items. So 8-year-old can tell you that sort of thing. And then you can answer a question like, how did he get wet? Well, in the stream, right? Yeah. What did he have on his boots? Mud, yeah, stuff like that. So the kid can answer those questions at age 8. Kid should recognize absurdities such as this. A man caught the flu twice. The first time he died, but the second time it wasn't too severe. And the kid should laugh, as some of you did. The rest of you will figure it out later tonight. Kid should laugh and say, that's silly. And you say, why is that silly? And the kid should say something like, because if he died the first time, then he wasn't sick the second time, he was buried because he was dead. And so he didn't get it sick a second time. And so if the kid says stuff like that, they say, okay, he understands. But if the kid says, no, that makes sense, he got used to it, you know what I mean? He doesn't understand the idea of died, right? And at the age of 8, they're supposed to understand that. Should be able to say something like this, what's the difference between an airplane and a kite? There are a lot of things a kid could say, right? So the kite needs the wind, or the airplane has a motor, or the airplane is made out of metal, or the kite is small. I mean, a whole lot of things. The kid should be able to tell you that. What's the difference between an ocean and a river? Kids should be able to tell you something like, well, the river water is sweet, or the river runs down to the ocean, and the ocean water is salty, but the river water is not salty, stuff like that. What makes a sailboat move? Go ahead, you can answer. What makes a sailboat move? The wind. Yes, kids should be able to do it. What should you do if there's a lost child? So a kid comes to you on the playground and said, I'm lost. What do? You tell a parent. You tell your mother, you tell the police, you tell some adult. Right? Name the days of the week. I won't ask you to do that. All right, that's 8. At age 12, the kid should be able to define words like these: haste, lecture, skill. Be able to repeat 5 digits reverse. So if I say 135, I want you to say 531. If I say 1492, you should say 2. And if I say 5, like 16578, you should say
8.
Yeah. Okay, that's 12-year level. Should be able to say what's happening in a picture. Should be able to define words like pity and curiosity. So what is pity? So these are emotion words. So by that age, kids should be able to supply missing words like Billy wasn't very tall, blank, he was heavy. But, however, something like that, that would be a missing word that would fit in. We should be able to recognize absurdities such as Johnny's feet were so big he had to put his pants on over his head. And the kid should be able to explain why that's silly. Well, because he would have his head sticking out the crotch or sticking out through the foot, and that would be embarrassing and stuff like that. All right, so those are the kind of tests. Now, his tests were in French. I just gave you the English version. So the English version was translated into English by a professor named Terman, who was a professor at Stanford. And he translated the test from French into American English, and in American English it gets called the Stanford Binet. Around the same time, the German psychologist Stern noticed that all the distributions for kids at different ages would have a mean of 100 and a standard deviation of 15 if he took the following ratio. So he defined IQ as 100 times mental age divided by chronological age. Now, mental age is going to equal chronological age for the average person, right? Because if the average kid can do these things at age 5, they have a mental age of 5, the average 5-year-old can do it, that means the average IQ is we're going to have a ratio of 1, so the average IQ is going to be 100. By definition, from the way the test items were created. And this thing holds pretty well up to about the age of 16. So this equation holds up to about age 16. And then after age 16, they simply call it an adult test. They give you the test that's devised for 16 or 18-year-olds. Some tests go on, keep making harder and harder tests up until you're about 18 or so. And don't try to correct for age. So if you just plot mental age as a function of people's ages, it goes up and then it levels off. People don't get any more items right after a certain point on these tests, after an age. And this value where it peaks over is somewhere between 16 and 18 years. We're plotting mental age as a function of chronological age. And Stearns noticed that if you take this ratio, you end up with a same mean, 100, and a standard deviation of 15 for ages up to about 16 years. So let's look at somebody who's age 10. Let's say somebody has a chronological age is equal to 10 years. But their mental age is like a 13-year-old. In other words, this kid is 3 years ahead of the average kid of their same age in terms of what they can do on a test. Well, then their IQ would be equal to times 13 divided by 10, that's equal to 130. So you now should be able to answer questions like this. What percent of 10-year-olds are 3 years ahead of the average kid? And the answer is, you already know the IQ distribution. You've memorized the areas under the normal curve. We know 100 corresponds to 0, 115 corresponds to a z-score of 1, 130 corresponds to a z-score of 2. And this becomes the question, if a 10-year-old has a mental age of 13, they have an IQ of 130, where is 130 on this distribution? 2.5%. So 2.5% of 10-year-old kids are 3 years ahead on average on this test. So they're like the average 13-year-old. 2.5% of 10-year-olds are like the average 13-year-old on this test. And suppose the person has a chronological age of 10 years, but their mental age is 7 years. In other words, on the IQ test, they perform like the average 7-year-old rather than like the average 10-year-old or 13-year-old. Well, then they would have an IQ is equal to 100 times the ratio of mental age divided by chronological age, and the mental age is 7 and the chronological age is 10, and that's 70. And so 2.5% of the kids at age 10 are 3 years behind, or like the average 7-year-old. That means if you have a class with 100 students in it, and just randomly picking kids, we've got a large classroom with 100, we've got 2 of them that are sort of 3 years ahead above the average, and we've got 2 of them that are 3 years behind, so we've got these kids that are 6 years apart with respect to items like that. Now, it turned out this test did a pretty good job of predicting success in school, and it got translated from any questions about chronological age, mental age, and the definition of IQ. Now, IQ stands for Intelligence Quotient. And why is it a quotient? Because instead of taking a difference, that's what Binet had been doing, he takes this ratio of mental age to chronological age, multiplies it by 100. It gets called a quotient. And when people talk about IQ, IQ stands for Intelligence Quotient. We get this number. All right. Any question about this equation? So you should learn this equation and how to use it. Any questions about it? All right. Now the Stanford Binet, the English version, they created, Terman created two versions with different items in it. And he gave the test to a group of kids and he calculated the test-retest correlation. So he gave them what was known as the L form with one kind of question. Maybe it had a story about the wet fall. And then he had another question like maybe Johnny goes shopping, you know. Mother sent Johnny to the store to buy some pickles. And he went to the store and they told him, we don't have any pickles. They came home without the pickles and his mother said, why didn't you bring home any pickles? And he said, because they didn't have pickles. What was the name of the story? Right? Some other questions like that. So there's the L form and the M form. And he had a group of kids take the L form and then the M form. And he found that they did a little better on the M form having taken the L form, but if they took the M form first, they did about as well as they did on that L form, but they did a little bit better the next time. But the key question was, what's the correlation between the L form and the M form? And he found that that was about 0.95. So the correlation, Rx, let's call it X prime, is a measure of reliability. That's how well can you predict from one administration of a test to another version of the same test, in this case using different items. And it was estimated for the Stanford Binet, so this is the Stanford Binet test. Was about 0.95. Is that a high correlation? Would you go to the store for 80% off? Would you go to the store for 85% off? So you're liking that as a correlation coefficient. Let's make sure we each had a chance to see these things. I already mentioned to you Binet's insight that brighter kids were like older kids. So he selected kids that distinguished kids by age, and he had success predicting success in school. And then it's Stern that comes up with this equation, mental age divided by chronological age times 100 is the intelligence quotient. And here's some results. We can ask about reliability. The alternate forms I just gave you, the L form versus the M form for the Stanford Binet is about 0.95. The test-retest with the same exact test, so I give you the L form, then I give you the L form again, it's a higher correlation a little bit, 0.97. If we look at different IQ tests, so there's the Stanford Binet, then there's the Cattell test, there's the Wechsler scale of intelligence for children. Wechsler also has another one that's for the adults, the Wechsler scale of intelligence for adults. There's various other tests that have been developed, some of them that people think are culture fair, that have more copying figures or matching whether figures are the same. There are tests that are more heavily laden with vocabulary or more heavily laden with matching, recognizing which pattern over here matches one of these patterns over here under rotation. We don't require so many words. All these different IQ tests correlate greater than 0.9 with each other. So there's a lot of arguments and debates about this culture fair test or the Stanford Binet or the Wechsler test. Many Cattell tests and various other tests have been created. All the tests tend to correlate with each other with correlations greater than 0.9. There might be important differences among them, but largely they're measuring something in common. Now, one of the questions that we want to take is an operational definition. Some people start off with some weird conceptual definitions of intelligence. Don't let those things confuse you. So if somebody tells you intelligence is an innate ability to learn, then what they're saying is intelligence cannot be influenced by the environment, a priori. And a lot of people would like that to be an empirical question, so they don't like that as a fruitful definition, is to define something that you don't know whether you can measure or not. So we're going to define a concept that we've never measured, like innate ability to learn, and then ask the question, this test is certainly not a test of that, because nobody knows what that is yet. So the operational definition is intelligence test is whatever it is that these IQ tests are measuring in common. And these tests seem to measure something in common. They correlate with each other. And so what do we mean by intelligence? We mean nothing more or less. This is an operational definition. What do we mean again by an operational definition? Operational definition is a definition that tells you how you're going to measure something. And in this case, the operational definition has to do with you give these tests and you ask if they agree with each other. To the extent that they agree with each other, then that's what we mean by intelligence. We're not going to try to add extra meaning to it. If you add extra meaning to it, you get yourself into debates that are a priori true or a priori false that people actually want to study as empirical questions. Now, I talked about the reliability of the test. The validity. What was the test supposed to measure? The question of validity is, does the test predict what it's supposed to predict? What was the test supposed to predict? It's supposed to predict success in public school. By public school is meant where you have one instructor and many students that are working at different levels. Now you can correlate IQ with GPA. GPA is grade point average. Grade point average has to do with teachers assigning grades to students, and the grades that teachers assign are based on a lot of different things. How much they like the students. If the students are well behaved, they may punish the students that are obnoxious by reducing their grades, whether the student's willing to do the work. So it's not necessarily a measure strictly of academic achievement, but it's supposed to be something like that. And the correlation between the IQ test and grade point average is about 0.6. Another way to measure success in school is by means of standardized scholastic achievement tests. Now, grade point average, these are the grades that presumably are based on the work that the students did during the year. The teacher gives tests, the teacher gives assignments, people do homework, they turn in the material, they get benefited by doing work. Scholastic achievement tests, typically the kid is measured one day a year or maybe over a 2 or 3 day period, and they take standardized tests of what's supposed to be in the, for example, the California curriculum. And so they will get out books and say, what is it that the kids are supposed to learn? They're supposed to learn how to multiply 2-digit problems. There'll be a lot of items on there answering 2-digit multiplication problems. They'll ask, how well did the kid do that? And the question is, can you predict which kids are going to do better at doing the multiplication problems, or know the facts about, in case of California, kids are supposed to learn something about California history. Know something about the mission, history of the mission system, Padre Serra, and various stories like that. And so these are scholastic achievement tests, and IQ is correlated, predicts those. So it predicts these two standards. Each of them can be criticized as not necessarily being a perfect measure of what it's supposed to be. The grade point averages are imperfect because they measure also the teacher's liking and whether the kid's willing to do the work, whether the kid is well behaved, and other factors besides how much the kid actually is learning. Scholastic achievement tests have the problem that a kid might be sick that day that they gave the test, or upset for some reason, or it's just a small measure of a person's performance, 1 day or 2 days, as opposed to over a longer period of time, like a grade point average might be based on a year's worth of work that the teachers give. So both these are imperfect, but that's what we have. Could you do better by asking a doctor or a teacher to predict what the grade point average would be or a scholastic achievement score is going to be? It turns out you ask the teacher to predict her own grades she's going to give at the end of the year, and believe it or not, the teachers get the kids confused. They don't remember, they don't have the grade book memorized. You know, sometimes students will approach me as if I've had the grade book memorized. I don't go through looking at score, at the ID numbers and scores and memorize this table. You know, the students have memorized their own score, but I don't memorize the scores. I look at the distribution, but I don't memorize individual scores. See, ask the teachers, how well is the kid going? What do you think the kid's grade point average is going to be? The teachers don't do a very good job of predicting what grades the kid's going to get. The doctors don't do a very good job. The IQ test does a better job. Is 0.6 perfect prediction? 0.6, so hopefully you've been learning something about correlation so you know a way to come to grips with a question like that. 0.6 means what percent of the variance?
36.
36% of the variance. Is that 100% of the variance? No, that leaves most of the variance still unaccounted for. Is it 0? No, so it's somewhere in between. So we have a device here, the IQ test, that's fairly reliable, that has some validity, and the validity can be characterized by this number of 0.6 that you need to understand some statistics to understand. You don't want to oversimplify it in one of two directions. You sometimes will hear in debates, the IQ test doesn't measure anything because I heard the case of somebody who had a really low IQ but they were really smart for some reason, or you will hear false information given. Well, Einstein had an IQ of 70 and he turned out to be a brilliant genius. That's false. He was a very bright guy. He did not have a low IQ, even though you will find websites claiming the opposite. He was autistic, everybody knows that. Had to be communicated with by a facilitated communicator. No, that's just a lie, that's not true. He writes about his own history as his father gave him a compass. He was fascinated by understanding what force was working on this compass that made it point north all the time, and that this problem bothered him all his lifetime, thinking, trying to understand what forces were at work on this compass. And his father showed him, if you put a ball in a wagon and you pull the wagon forward, the ball looks like it goes backwards. He was trying to explain to him the concepts of inertia, and he was working on these problems, trying to understand them at age 5 and so on. So some of these anecdotes you hear are wrong, but some of the political polemic, and there's a lot of polemic that has happened, some of which you may have heard, people exaggerate or understate the validity of the IQ test. You should not shrug them off as measuring nothing, and at the same time should not assume that they are that you could do better by asking a teacher or a doctor or somebody to interview the kid and do a better job. Now you can ask this sort of question: are these tests biased? And the question of test bias is one that people, when they take a class, haven't really thought about the definition of bias. So let's talk about the definition of test bias when it refers to group biases in test performance. And I told you already that what we talk about in here is on the cover of the Times. Well, it was already a couple days ago, but what's been a big issue on the cover of the Times lately? How they hire firefighters. So let's use that as an example. There's been a big scandal going on in the hiring of firefighters for the LA Fire Department. Anybody read about it? Oh, that's right, you don't read the newspapers. I recommend it, they're free. You can go over there. It's right now you're trying to decide, do I want to stay a kid forever or become a participant in our society? Find out what's going on in the world and get involved and vote and pay attention to what's happening in society, or just remain a kid and be sheltered from thinking about all these difficult problems that parents and other folks have to think about. Well, one of the things that's going on in the world right now is how should you hire firefighters? One of the scandals I won't talk about is some people have cheated. We won't deal with that for right now. But let's talk about whether or not there's biases that might be in the test. Sometimes we're interested in group biases, ethnic differences, religious differences, gender differences in hiring. And so here's the definition of test bias. So here's the test score. And here's the criterion of what it's supposed to predict. And if we're thinking about hiring firefighters, what do we want the firefighters to be able to do? We want them to be able to do the job, right? That's the criterion. We want to predict a person being able to be successful as a firefighter. Should you require firefighters to be able to read a map or understand directions? Well, some people say, no, that would be bad because some people aren't good at reading maps and that would be unfair to them. I'd be biased to ask firefighters to read them. Well, what does a firefighter have to do? When there's a fire, what happens? People call up and they say there's a fire at 112 Elm Street. And what do the firefighters have to do? They have to jump on the wagon and drive there, right? And if they go driving off and are lost for 2 hours, finally show up, oh, Elm Street, I thought it was the same as Maple Street. No, it's Elm Street. I wasn't able to read the map and I couldn't really, oh, that's right, we have GPS, but the GPS was out, so we couldn't find our way, to the fire. They have to get there quickly, right? So they have to be able to understand an address and be able to figure out where it is and figure out how to get there. So we might have a test of being able to understand, how to find where 112 Maple Street is on a map and how you would get there from the fire department. Should a firefighter be able to do pull-ups? People say, yeah, but women can't do very many pull-ups. Men can do more pull-ups than women. So they don't require firefighters to do pull-ups anymore. But they do ask them to drag a 185-pound sack. And the question is, if you have a burning relative who weighs 185 pounds, do you want the firefighter to be able to drag them out of the burning building or not? And maybe strength is an important thing. Should a firefighter be able to hold onto a hose that wants to jump out of your hand and go flying around? They might need to measure strength in some way. People will claim, well, the test is biased because women, on average, aren't as good at holding onto a moving fire hose as men are, or maybe they're not as good at reading a map. But a woman who can read a map just as well as a man, should she be able to be hired? We want to find out, is the test itself inherently biased, or does it predict success as a firefighter in the same way for both genders? So we can put 2 groups on here. Here's a situation where here's group A and here's group B, let's say. And here's the relationship between the test score and the criterion. So this might be job performance. If we're trying to hire a firefighter, this might be success in law school. If we're trying to predict who to let into law, is the LSAT, the law school admission test, is it biased against some groups? This might be an IQ score down here, and this would be grades up here. So the question is, does IQ score predict grades the same for both groups? Well, here we've got, for group A, we see there's a nice correlation between the test and the criterion. And for group B, you see a correlation between the test and criterion. But this shows us evidence of some kind of bias. Now, which group is it biased against? And here's the definition. For the same test score, do members of one group do better on the test than predicted from the criterion? And in this case, it looks like members of group B do better on the criterion than members of group A for the same test score. So in this case, this one's biased against B. And as a matter of fact, the group B is doing better on the job performance than group A, even though they're doing worse on the test. In this case. How about this one right here? Well, let's see, let's put group A here and let's put group B here. Group A does better on the test than group B. So here's group A, A's mean down here, this is group A, and then projecting these points down here, this is group B. So group A does better on the test than group B, but is this biased against A or B? You don't just look at the test scores down here, because group A is doing better on the test than group B. Does that mean it's biased against B? Here's the criterion going this way. Which group is this biased against? Well, what we do is we look at, for a given test score, which group is doing better on the test, and it's group A that it's biased against in this case. Even though they do better on the test, for the same test score, let's say we take this test score up here, group A is doing better on the criterion than group B, so this one is biased against A. And I recommend you work through a lot of examples like this until you understand this. You need to know both a test and a criterion and the relationship within each group. How about this kind of situation? This one should be easy. The two groups do equally well on the test. Is this one fair or unfair? So this is group A and this is group B right here. Is this a fair test or not? Both groups do equally well on the test. But for the same test score, members of group A are doing better than B. This one's biased against A, even though if all you did is look at the test scores, you'd say, oh, the test is equally, both groups are doing equally well on the test. But they're not doing equally well on the criterion. So this one's biased against A. Here's one where A is doing better than B on the test, but for the same test score, they're doing equally well. This one's unbiased. All right, so you need to distinguish between cases where maybe groups differ on something like strength, and strength is relevant to being a firefighter. And you can hire then the strong women, even though the average woman is not as good as the average man that takes this test. There are women that should be hired, and the test in this case might be equally good for men and women. So this one is an unbiased test, even though there are group differences on both what's on X and on Y. There can be average differences, but the key is, do the two groups fall on the same regression line, basically? Do they fall on the same relationship between X and Y, even if there are group differences on both X and Y? So you need to work through these examples to understand. Again, do not bring the naive kind of thinking about test bias in here. And there's been a lot of people getting really excited about trying to not worry about group differences that show up on IQ tests because they say, well, let's just forget about it because we'll pretend that the test is biased and therefore we don't have to think about it. And that's sort of like trying to sweep under the rug, kind of like what's happening in Florida. Read the newspapers, what's going on in Florida right now? What's happening in Florida? You're not allowed to talk about global warming or climate change or sea level rise. These are forbidden. If you work for the state of Florida, you're not allowed to talk about these things. They issued a gag order that state employees are not to talk about, not to use the term global warming or sea level rise. Why? Because they don't like the problem, and they think if you just don't use the words, the problem will go away. It's kind of like trying to legislate the value of pi to make it 3 or something, From now on, no child will be left behind. We're going to pretend that we can pass a law that no kid will fall behind